Let us study the contour integral definition of the theta function. And theta function appears in the time-ordered product in the time-dependent perturbation theory. We will find that it is convenient to reparameterize this theta function as an integral. In short, theta function can be defined to be limit as epsilon goes to plus 0, I over 2 pi, integral from minus infinity to infinity, exponential minus I omega t divided by omega plus I epsilon. The sign is very important. This epsilon must be positive, and the integration is over d omega. We can rewrite omega as energy divided by h bar, and this integral can be rewritten as an energy integral. This is the integral from minus infinity to plus infinity, that is along the real axis, and we can obtain the contour integral along a closed contour. And let us define this contour integral like that. I equals I over 2 pi, contour integral along a closed path, minus exponential minus I omega t divided by omega plus I epsilon d omega. And this is the contour I introduced. This is a C plus and this is C minus, where R is a very large number from minus R to plus R, and the contour can be closed on the upper half plane or lower half plane. If we close this contour, the integral vanishes because of it. There is no residue inside. And if we close the contour along the lower half plane, then this integral is non-zero. The problem is that whether this contour integral is exactly the same as the integral from minus r to plus r, where r goes to infinity. So we will find that if t equals negative, then the integral along this semicircle on the upper half plane vanishes, and if t is positive, then the integral along a lower half plane, along this semicircle, vanishes too. And as a result, if we integrate along this closed path, that is 1, and the path, this lower path, is 0, so the integral from minus infinity to infinity becomes 1 if t is positive. And if t is negative, actually this integral is 0 always, but if t is negative, then the integral on the semicircle on the upper half plane vanishes, so integral from minus infinity to plus infinity becomes 0 for negative t. So in summary, if t equals t is positive, then the integral along the real axis is the same as the integral on the lower half plane, and that is 1. And if t is negative, the integral from minus infinity to plus infinity is the same as the contour integral, that is closing the contour on the upper half plane, and that is 0. So as a result, theta function can be written like that. So let us prove that. First of all, we have to find the residue, and we find that the residue appears only at omega equals minus I epsilon. So at omega equals minus I epsilon, the residue can be found by substituting omega with minus I epsilon. Okay. If I substitute minus I epsilon without this factor, I have I over 2 pi, that is the overall factor, and omega is substituted with the minus I epsilon here. If I substitute minus I epsilon, the result is I over 2 pi exponential omega is minus I epsilon, so epsilon t. Okay. If t is finite, because we are taking the limit epsilon goes to 0 plus, this value, this exponential becomes 1. Therefore, the residue is I over 2 pi, right? This is 1. Therefore, if we close this contour on the lower half plane, the integral has the residue, and whose residue is I over 2 pi. If I close this contour on the upper half plane, there is no residue at all inside the contour, so the contour integral vanishes. That is independent of the value of t. Whether it is positive or negative, those contour integrals are well defined. Okay. On the path C plus, the integral is 0 for the closed contour, and for the path C minus, the integral is always 1. Why? Residue is I over 2 pi, and I multiply 2 pi I, and the direction of rotation, the path is along the clockwise direction. I have put a negative sign here. So if I multiply these two factors, I have exact 1. I'd like to verify that if t is positive, the integral along this lower half plane, especially on the semicircle, vanishes. And if t is negative, the integral along this semicircle vanishes. So if I prove that, then those contour integrals are same as those integrals. So if t is negative, integral is 0. If t is positive, this integral is 1 to get the theta function. Okay, this is the most important part for that derivation. We use the Schwarz inequality. Let us consider just this core part of the integral. And because we want to show that that integral vanishes, it's sufficient to show that the absolute value of that integral vanishes. So, our plan is to take the absolute value of that definite integral on the lower semicircle, and that is this without this over factor, and absolute value of an integral is here. Okay, I have substituted the value of omega on the semicircle on the lower half plane. Complex number omega can be parameterized by r times exponential minus I theta. Because this angle runs from 0 to minus pi, if I parameterize this complex number to be exponential minus I theta, then theta runs from 0 to pi. So theta runs from 0 to pi. Let us take the differential of omega. Then I have minus I factor and r e to the minus I theta d theta. So as a result, d omega can be written as minus I omega d theta. If I multiply this one, if I substitute this value in here, the integral along this lower semicircle has no pole at all, because this is omega and this is omega. They cancel. There's no pole because the pole is only at omega equals minus I epsilon. So they cancel, and let us substitute omega with r e to the minus I theta. And r e to the minus I theta is actually r cosine theta minus I sine theta. If I substitute that and expand it, and I find that it is minus I r cosine theta and minus r, it is real part, minus r sine theta t. Alright, so this absolute value of that integral is always less than the integral of the absolute value of the integrand. Then if I take the absolute value of the integrand, this over factor exponential minus I r cosine theta disappears.